Hi everybody, welcome to the lesson in which we introduce the language of statistics and sampling a little bit too. To get started, most of the time in statistics we're interested in a population. And a population is all of something. It could be people, a lot of times it is, but it doesn't have to be. It could be objects, it could be businesses, it could be government entities, it could be some kind of event. But what's important is that it's all of something. Within a population, we're usually interested in looking at different attributes, different variables. And within a variable, there are different values. So let's look at some examples. A population might be all elementary schools in the United States. And a variable might be the number of employees. And it's important to be aware of what your population is. For one thing, because when you're looking at your data, this tells us that every row in the data is going to represent an elementary school. So it's important to realize when you're looking at the average of this variable, you're looking at the average number of employees in the elementary schools in your data set. Another example might be if you're looking at all of the Facebook posts in a given month. Whether that post is personal about somebody's life, or if it's more general, politics, weather, memes, stuff like that. And for something like this, it's important to realize that in the data set, every line of data, every row of data represents a Facebook post. So when we look at, the proportion of them that are personal, that's the proportion of the values in our data set that are personal as opposed to general. And then a final example, inmates in prisons in North Carolina. We might look at, for those prison inmates, the number of upper respiratory infections they get per year. So in that data set, every row of data would represent one prison inmate. So now, talking about a sample, ideally, we'd be able to get information on every element in the population. But a lot of times that's not feasible. Sometimes it's just not possible. If we wanted information on every fish in the Pacific Ocean, for example, it would be impossible to get information on all of those. So what we have to do instead is take a sample. So a sample is just a smaller version of the population. And we hope that the information in the sample is just a smaller version of the population, that it has those same characteristics as the population. So a parameter is some numeric characteristic about a population. A statistic is some numeric characteristic about a sample. So parameter, population, statistic, sample. Okay, that's easy to remember. Some examples might be, a parameter might be the population mean, whereas the statistic might be the sample mean. Parameter might be the population proportion of something. Statistic might be the sample proportion of something. And because a statistic is based on a sample and a parameter is the same thing for a population, statistics are our best estimate for parameters. So statistics and parameters come in pairs because, every time there's a parameter we want to know, there's a statistic that we use as an estimate. I want to go ahead and give you these two symbols because these are going to come up from now until the end of class. So you might as well memorize these. This Greek letter that looks like an M is a mu. And that's the symbol for the population mean. This other one is called X bar, and that's the symbol for the sample mean. In general, Greek letters usually represent parameters. Okay, so this is mu, the population mean, and then X bar is the sample mean. So you probably want to write those down and keep those handy, or better yet, just memorize them. The quicker you can, the better off you'll be. So continuing on, let's look at that example we talked about with prison inmates. If we want to estimate the mean number of times per year they get an upper respiratory infection, we might take a sample of 1,000 inmates and keep track of them for a year. And suppose we find that the sample mean is 5.2 upper respiratory infections per year. So this is based on the sample, so that would be a statistic. Therefore, our best guess for the parameter for the population mean is going to be 5.2. Okay, so we don't know the value in the population, but our best guess is 5.2. So we've made a generalization from the sample to the population. And another way to say that is an inference. So we've made a statistical inference from the sample to the population. And that takes us to the whole branch of statistics, which is called inferential statistics. And inferential statistics is just a set of statistical methods that uses information in the sample to make those generalizations to the population. We can do things like, say, create an interval that we are 95% sure contains the true value of the population mean. Or we can say, based on this data that we have, is it reasonable to assume that the population mean is less than 6 upper respiratory infections per year? So that takes us to a course outline. So in the first unit of the course, we'll be doing descriptive statistics. Descriptive statistics is a set of methods used to describe data. So we'll be looking at things like proportions of the sample. We'll be looking at measures of center, so mean, median, mode, how spread out the data is, and then we'll be looking at charts and graphs. So that's descriptive statistics. Next, we're going to do some stuff with probability. And we don't spend too much time on that, but that's important because it lays the groundwork for these inferential statistics, which is basically the second half of the course. We'll be doing statistical inference and looking at those things that we talked about a minute ago. So, next let's talk about different types of data. This is going to be very important for us because part of our job the rest of the semester is to identify, when you look at data, what's the best procedure, the best kind of methods to use on the data. Should you be calculating a mean or a proportion based on this, for example? Which type of graph do you need for this kind of data? And it's the type of data that either completely determines or at least is part of the consideration of which type of statistical method you use. Okay, so the type of data is going to be a determining factor there. So when we look at a variable could be qualitative or quantitative. So qualitative means categorical, so it's not numeric. Quantitative is numeric, the quantities versus qualities. All right, so if we've got quantitative data, that's numeric. Qualitative data is also called nominal. So nominal level data is is synonymous with qualitative or categorical. Quantitative, though, can be broken down further into ordinal, interval, and ratio. So let's talk about each one of those. So first of all, qualitative data. That's that categorical data, things that have labels but not numbers associated with them. So somebody's major. And I put this one in here, these last two, to show you that a qualitative variable, a nominal level variable, can still have codes attached to them that are numeric, but it doesn't make them numeric data. So if you look at something like Democrat, Republican, unaffiliated, those are still nominal level values, even though they're attached to 1s, 2s, and 3s. And if you think about it, does it make sense to average those together? If you took an average of a bunch of these values and got 2.4, that doesn't really tell you very much, or anything really. So think about, does it make sense to average those together? And then the same thing with driver's license numbers. Those numbers don't represent something that's numeric. Those are just labels. So now let's talk about quantitative data. We said there are 3 kinds of quantitative data. The first one is ordinal level. So with ordinal level, the values represent order. Class rank is an example of those, first, second, third. And when we say that the difference isn't meaningful, in somebody's class rank, there could be very little difference between the GPAs of the person who got first and second, but very big difference between second and third. It doesn't matter what those differences are. Class rank doesn't tell us that. Class rank only tells us what order it's in. But now with class rank, you can only have one person who's number 1, one person who's number 2. There are ordinal level values where you can have more than one of each. So something like educational attainment. The difference between somebody with less than high school and high school is not the same. There's not a meaningful difference between that. Same thing here, high school to college. It's not like, there's a difference of 2 years between 1 and 2, and also a difference of 2 years between 2 and 3. So educational attainment is only measured, according to the way this is defined, as a first, second, third, fourth. Okay, and ages of adults are the same when they're categorized this way. If what you had was the actual raw data about a person's age, that would be different. That wouldn't be ordinal level. This is ordinal level because they're categorized, where all we know is these are the youngest, these are the, let's call these youth, adult, middle-aged, and elderly. I hope that's not insulting to anybody. Anyway, but you get the idea. So all we know is what order this is in. Okay, so that's ordinal level data. So now let's talk about interval level data. Interval level data is a step up from ordinal level data, meaning it gives us a little bit more information. That's because if we look at successive values on an interval level scale, they represent the same difference. So a difference of 1 degree, from 1 degree to 2 degrees Celsius, represents the same amount of difference as 1 to 2 degrees. And the same thing is true on the IQ scale. An IQ difference of 100 to 101 is the same difference as 101 to 102. We talk about there being no natural zero and ratios being meaningless. What that means is that 0 is sort of at an arbitrary place on the scale. This is usually when we've got a scale that somebody has imposed on something. These are not weights and measures. Things that you can measure with a measuring tape. So there's no natural 0 because on the Fahrenheit or the Celsius scale, somebody just said, okay, let's put 0 at this place. Okay, same thing with IQ. Now, when we say ratios are meaningless, somebody with an IQ of 100 is not twice as smart as somebody with an IQ of 50. So it doesn't make sense to talk about somebody being twice as smart. And the same thing is true with heat. If it's 100 degrees Fahrenheit, that's not twice as hot as if it's 50 degrees. Okay, so those ratios don't make sense to talk about. Finally, let's talk about ratio level data. Ratio level data gives us the most information. There is a natural 0, something like the number of questions answered correctly on a test. If that is 0, that means that you answered 0 questions correctly on a test. And it makes sense also to talk about the ratios. You know, if you got 2 questions right, that's twice as many as if you got 1 question right. And the same thing is true with distance and time. Now, when we say time, time means the amount of time. So 2 seconds is twice as long as 1 second. One specific type of data I wanted to talk about is a Likert scale. So the Likert scale is when we say strongly, disagree, etc. Likert data is actually ordinal, but a lot of times it's treated as interval. And in fact, some textbooks will tell you that it's interval, because a lot of times researchers will assign values to these. So like strongly agree is 1, agree is 2, neither is 3, etc. And then they'll take those averages. So that's a convenient thing to do. It's not great to do that statistically, but it's still very common to do. So take a minute here and go through these 4 and see if you can identify what the level of measurement is for each one of these. So pause the video, take a sec, and give yourself a little bit of practice here. All right, so here are the answers, and here's why. So the speed a car is traveling is a ratio level value. That's because there is a meaningful 0 there. So first of all, it is numeric. So that's a numeric value. There is a meaningful 0 there. So if you're going 0 miles per hour, it means you're not traveling. And you could talk about, somebody going twice as fast. So that's a ratio value. Stage of development of a person, that's ordinal, because it's sort of numeric. There's a ranking there. Infant would be the first stage, toddler would be the second stage, etc. But there's not a meaningful difference between these values. The difference between infant and toddler is not necessarily the same as the difference between toddler and child. The third example, the year in which an event occurred. Now, we said time was ratio. The year in which something happened is interval, though, because there's not a meaningful 0. Okay? So 0 BC AD, that doesn't mean there's 0 of something. And if you look at, the year 2000 versus the year 1000, that's not twice as much of something. So that's interval. Finally, for a given home, the high school district where it's located, that's nominal. So your home is in, the district for this school or that school or the other school. All right. So now, moving on, let's talk about sampling a little bit. So sampling, we said that the sample is the basis for all inference to the population. So it's important that we get a good quality sample. And that means a sample that is representative of the population. That's the same as the population, but just a smaller version of it. So sampling bias is when the sample isn't representative. And when that happens, we can't get valid inferences, valid generalizations to the population. In this picture, we've got, this is Harry Truman back in, I think it was 1946, when he ran for president against this guy named Dewey. I forget Dewey's first name. But there was a telephone survey that was done, and the telephone surveys all predicted that Dewey was going to win. And what happened was, back in 1946, it was really only the wealthier households that had a telephone. So when they did the telephone surveys, that only revealed how many of the wealthier households planned to vote, or how they planned to vote. And that skewed the results, so they didn't get a representative sample. So the way to decide if you've got a representative sample, because the whole point of taking a sample is because you don't know the population. So you can't just look at the sample and say, oh, that looks like it's similar to the population. What you have to do is consider the sampling process. Is this a sampling process that is likely to yield an unbiased sample? And so you ask yourself, am I sampling in a way that some elements are going to get overrepresented and some are going to be underrepresented? And in this case, that's what happened. The wealthier people got overrepresented in the sample, and the less wealthy people were underrepresented. And that made the prediction incorrect. And that's one thing that has happened, some of our recent elections where we've seen predictions that are incorrect. That's part of why, is that it's hard to get a good sample because of issues with surveys. More on that in just a minute. So there are some different sampling methods that you should be aware of. The first is simple random sampling. In simple random sampling, this is the best kind of sample there is. This is the one where it's the least likely to yield a biased sample. With simple random sampling, every possible sample of size n, and n is another one of those letters that you should know, n always represents the sample size, has an equal chance of being the actual sample chosen. Usually this requires a random number generator. And the way we would do that is, if I wanted to take a sample of all Queen's students, I might assign each one of them a random number using a random number generator. And then I would put those random numbers in order. And if I wanted a sample of 500 Queen's students, I would take the people with the 500 lowest random numbers. Okay? We could draw names out of a hat, but nobody really does that. We use the random number generator to do that in a more technological way. So that's simple random sampling. Random number generator, and use the random numbers to choose. Next one is systematic sampling. And in that one, you have a list of the population, and you sample every, say, 10th element on the list. This is a pretty good sampling method most of the time. You have to think pretty hard to come up with an example where you could get something biased. But if we wanted to do this with Queen students, we might take a list of all Queen students, and every 25th person on the list, we would end up in our sample. Like I said, it's hard to come up with an example where there might be sampling bias there. If we've got people arranged in a certain way in a room and we took every 5th person, and it just so happened that every 5th person, the way the classroom was arranged, that got all the people in the back of the room, that would be sampling bias there, but most of the time this is pretty good. Stratified sampling, you've got the population being divided into groups, and then you take a sample from each one of those groups. So an example here, if we wanted to take a sample of Queen students, we might break it up into people who are majoring in STEM fields, people who are majoring in business fields, people majoring in health fields, etc. And we might take a sample from each one of those. So a sample of STEM majors, a sample of business majors, etc. So that would be an example of stratified sampling. Cluster sampling is different from stratified sampling, but people get these two confused. With cluster sampling, you're dividing the population into groups again. But instead of taking a sample from each of the groups, you're choosing just a few of the groups. And within those groups, you're sampling the entire group. Okay, so an example of that might be if we randomly select biology majors and communication majors and accounting majors. And all of those people represent our sample of Queen students. Okay, this one can sometimes have its advantages, but it's not as good as some of the other ones. Okay, so again, the difference between systematic and cluster sampling is that, stratified and cluster, is that with stratified sampling, you're taking a sample from each group, whereas with cluster sampling, you're taking all of just a few of the groups. Finally, convenience sampling. With convenience sampling, you're just taking your subjects because they're convenient. So convenience sampling might be if I walk around campus and just sample whoever I happen to find. Or if I take a sample of, just the people who are in my class. This is a really bad way of sampling. This is not likely to get a representative sample. All right, so take a minute and see if you can get some practice. Okay, so pause the video, take a minute, and decide which type of sampling you think either one of these is. All right, so now let's go over those. So we want to take a sample of people who work in a large hospital. So we sample every 25th person on a list of all the hospital employees. That's systematic because we've got our list and we're taking every kth one. Waiting outside the hospital cafeteria and sampling employees as they go in, that's a convenience sample. This one, dividing employees into categories and taking a sample from each one of those, that's stratified. So we're taking a sample from each one of those. With cluster sampling, we're dividing into categories again, but this time, for 4 of those categories, we're sampling everybody. And finally, with this 5th one, we're using the random number generator. That's a simple random sample. So now in terms of whether each of these is representative, if we look at every 25th person on an alphabetized list of all hospital employees, there's no reason really to think that the people who end up in that sample are different from the ones who don't. So I think that one is sound. Convenience sampling is always problematic. If you think about who ends up in the sample versus who doesn't, people who work from home don't end up in the sample. People who drive to have lunch off-site, those are not going to end up in the sample. And then people who brown bag it are not going to end up in your sample. So could those be different? Entirely possible. Because they self-select. Dividing employees into categories based on their job and then taking a sample from each one, that's pretty good. Making sure we get a sample of housekeeping, a sample of people who work directly with patients, etc. That's probably good. Now, if we decide that we're going to pick 4 categories and we sample everyone in those, that should be 4 categories, that would be a cluster sample. And there might be some reason you'd want to see that. You might want to get a, say housekeeping was one of yours. You might want to make sure you're getting people of all levels within housekeeping. And the same thing with accounting. Maybe that's one of the ones you decide. But that's cluster because you're sampling everybody in those categories you pick. And finally, the simple random sample, that is, that's the perfect example. That's the ideal. One more thing I should mention, anytime you've got a survey, there's going to be non-response bias. And that's because not everybody answers the phone. Not everybody mails the survey back. Not everybody answers the email. So when that happens, the people who opt out are very different from the people who opt in, usually. So it's hard to get a good sample when you're doing a survey. So as we said, sampling bias is very important on interpretation of results. And what that means is, say we go back to this convenience sample here. The only way we can, in a valid way, generalize to the population, we really only got a sample of people who eat in the school cafeteria or in the hospital cafeteria. We can't generalize that to all hospital employees. We can only generalize to people who eat in the hospital cafeteria. So we have a limited inference that we can make there. All right, so that's it for this lesson. Keep working. Keep trying to familiarize these terms. And if you have any questions, as always, please feel free to reach out to me. I'm always happy to answer student questions. All right, enjoy.